Assalamualaikum warahmatullahi wabarakatuh.
Today we're going to explain about quadcopters, how they function, and how they're used for, and then on to the explanation.
From helicopters to quadcopters, deciphering the dance of drones. In the realm of aerial vehicles, helicopters stand out with their intricate control system featuring dual rotors and swash plates. On the other hand, quadcopters bring simplicity to the skies with 4 equally spaced rotors. Recent strides in affordable microprocessors have ushered in the era of electronic and autonomous control for quadcopters, revolutionizing their applications. But here's the fascinating puzzle. Quadcopters boast 6 degrees of freedom, yet they're controlled by just 4 independent rotor inputs. This imbalance sparks a web of complex dynamics and intricate aerodynamics effect. Unlike ground vehicles, quadcopters glide through the air with minimal friction, necessitating the generation of their own damping forces for stability. Engineers navigate this complexity by crafting simplified models and controllers to chart quadcopters' designated flight paths. They subject these flying marvels to rigorous numerical simulations to ensure precise control and stability.
In the realm of drone kinematics, on the other hand, the angular velocity vector in the body frame reveals its complexity through a matrix derived from the ZYZ Euler angular conventions. This matrix seamlessly connects the dots between the drone's body frame, angular velocities, and the time derivatives of the roll, pitch, and yaw angles. Now, to align the body frame with the inertial frame anchored to the ground, engineers employ rotation matrix. This matrix is a product of the ZYZ Euler angle conventions that translates the drone's body frame and angular velocities into inertial frame, providing crucial understanding of its orientation relative to the Earth's reference frame.
Unraveling the physics. Diving into the drone's physical aspects, we discover the heart of control, and that is torque generation. The torque equation, T equals KT IO, unveils the intricate relationship between torque and current. It showcases how torque depends on the difference between motor current and a base current, playing a pivotal role in controlling the drone's orientation and stability. But that's not all. Understanding voltage drop across motors is a must, described by V equals IRM kV omega. This equation underscores the significance of voltage drop in drone operation. It illustrates the interplay between voltage, current, motor resistance, motor constant, and angular velocity, all critical for efficient power management and flight responsiveness. Total power output emerges as a key player in drone performance. P equals T KT IO kV omega KT provides an approximation of the power generated. It reveals how torque, motor current, and angular velocity collectively impact the drone's overall power consumption, pivotal for maximizing flight time and performance. Here are some equations of motion. Euler's equations gracefully dance through the dynamics of angular momentum change, external torques, and the drone's rotational motion. This equation encapsulates the essence of controlling the drone's intricate rotations. This equation seamlessly integrates into the drone's flight equation in the body frame, featuring the rotational matrix and the diagonal inertia matrix. Together, they form a comprehensive understanding of the drone's rotational dynamics. Considering its orientation and arm configuration, it's the cornerstone of controlling the drone's aerial ballet. And there you have it. From the complexities of rotor control to the elegance of kinematics and the interplay of forces, drones represent the convergence of technology, engineering, and physics, all soaring high in the boundless skies.
So now I'm going to be explaining how PID works in the context of a quadcopter, and I'm going to try to simplify it in a way so you can understand it. So PID stands for proportional integral derivative, and it's basically a component of the quadcopter's control system. Its function is to help maintain the quadcopter, maintain stability, and respond to changes in such as the wind or drag effectively. And at its core, it calculates a signal by continuously monitoring the error between what the control system wants and what the value of the control system actually is. And the following you can see a block diagram, and I'm going to try to simplify the main 3 points of the block diagram, which is the proportional, integral, and the derivative. So the proportional term provides basically an immediate response to the current error, and whatever error it does, it adjusts the system based on how like the magnitude of the error. And following that, we have the integral term, which considers the cumulative pass of all the errors, and it calculates to make a long-term basically model on how to manage the errors and biases. And the final is the derivative term, and what this does is it anticipates future errors by looking at the rate of change between the previous errors, and this helps to dampen sudden abrupt changes within the quadcopter. And these 3 terms are then combined to create what we call a control signal, which is then sent to such as the quadcopter's rotors, and this creates stability and response to external influences. So now I'm going to be demonstrating the principles that we discussed in the material previously on an actual quadcopter. So a quadcopter stabilizes and moves by manipulating the speed of its 4 rotors. To maintain stability, it relies on a combination of 2 principles, which are balance and torque. By adjusting the rotational speed of each rotor, the quadcopter can create an equilibrium force for itself. For instance, if it wants to hover in place, it makes sure that all rotors are spinning at the same speed. And if it, for example, wants to move forward, what it does is it needs to tilt needs to tilt the quadcopter forward. So to do that, what it does is it reduces the thrust of the forward rotors and increases the thrust of the backwards rotor. This makes it move forward. But why doesn't the quadcopter simply spin in place during normal flight? This is because the rotors itself are designed to create opposing forces to each other. So what that means is that on a normal quadcopter, each rotor is spinning in an opposite direction to itself. So this one is spinning in clockwise, this one is spinning in counterclockwise. And that's the same for the back rotors. What this does is it creates an opposing force that maintains the balance.
In the realm of drone dynamics, we've unraveled the science behind PID control. These techniques wield proportional, derivative, and integral gains to orchestrate orientation and stability. Matrix form unify these equations, enabling drones to soar confidently and adapt seamlessly. And that wraps it. Thank you for watching our video, and have a nice day.